Okay, so what we gonna do in this video is just it's a revision video for all the DSA I have studied till now. It's not that much I know, but let's see. So I just want to connect every knowledge I have in one single thing, video or note you can say. So I will be dictating the things, or you can say revising the things and writing it here in this whiteboard now. So some basic things, everything is basic, but some of the things I want to mention is first is the swapping of two numbers without using third variable. So in this we will do it by using XOR. So by XOR what we will do is A equals to A XOR B, B equals to A XOR B, and now A equals to A XOR B. Doing these three things will give our answer as swapped A or B. Now let's elaborate how this happened. So here we simply say A XOR B. Now here we will replace A with A XOR B. So we will have B equals to A XOR B XOR B. So combining these two we will get B equals to A. Okay, and now doing the same for this. A equals to A XOR B. Okay, so now we know that this A XOR B is not what, this is just A XOR B. So now A XOR A, this will become A equals to B. This is the first thing. By doing these three things we can get swapped A and B. So now let's move to another thing. This was A. Now we will study the DNF algorithm. So what DNF algorithm says is that DNF ergo, and what is the full form of DNF? It's Dutch National Flag. Okay, so this algorithm is used in questions like there is a one particular question on based on this algorithm, which is sort 0 1 2. I don't know why I did. Okay, so sort 0 1 2. This is one question which uses the DNF algorithm. So in this type of problem what we do is, we first imagine the array, given array. We have been given array of like 0 2 1 1 2 0 0 1 2 or 0. So we have been given array like this. We will imagine first that the array is divided into three parts. The first part will have a I can say this will be like a 3-pointer type thing. DNF and go is basically 3-pointer. Okay. If we have been given sort 0 1, then it will be 2-pointer. DNF algo is 3-pointer. So we will think it like this. Start with a pointer start, a pointer mid, a pointer end. Start will be the basically end point of 0. This will be traversing through the array. Mid will traverse through the array, and end will be start point of 2. Traversing through array, and mid will also keep track of ones present in the array. Okay, so now we know how this works. So what we'll write is, if mid equals 0, not mid, where what I want to say is ARR mid. ARR mid equals 0, then simply swap ARR start ARR mid, and also increase the pointer start plus mid plus. Basically start will be from the before entering the loop. Start pointer will be pointing to 0, mid will be pointing to 1, and end will be pointing to n-1. Okay. So what I want to say is, start 2 mid -1 will be 0, mid to end -1 will be 1, and end to n-1 will be 2. Okay, so this I want to create in minimum time complexity. So if let's keep it inside this will be our starting condition. If mid equals 1, then just increase the mid pointer. If mid equals 2, then do the same thing that did here with a little bit of change. I'm telling you what change it is. So what change it is that wait, first of all I also need to change the mode of this annotation. Okay, so okay, so now yes, swap not start and not this, but ARR and minus minus. Got it? So this is the complete algo. Also take care of one thing, that we don't swap mid, we don't increment the mid here, because what will happen if think it like, if the end pointer had 0, like we swapped the mid with end, but what if this, I'm highlighting this so you can get better, what if this pointer is 0, and if we increment this, then obviously we can't get the desired value what we want. Like what I want, it's simple, that I want to get 0 in the start, 1 in the mid, and end in the 2 in the end. So if this has 0 and we swap, then we can't get 1 in this in the mid, and we will have 1 0 staying in the mid pointer, which is wrong, and it will give us wrong answer. That's why we will not increment the mid here. Similarly, what will happen if we swap the start with mid and start with mid, swap start with mid, and start has 2, then mid will also have 2, and it will also give us wrong answer. That's why we will also not increment this here. So it means that we'll only increment the mid if we get 1 in the mid. Okay, and if we don't, then we will just swap and increment or decrement start and end pointer respectively. Now we know what we have to do. So let me just do this thing. So now we have this. Now what we can do more is, first of all, let me draw a line. What happened to this? Leave it. So we have this Dutch algo, we have this swapping. Now let's learn something else. Now let's study modular arithmetic. Modular arithmetic. So we got some formula in modular arithmetic, like first of all we should know that A plus B modulo M and A into B modulo M follow same formula. So we will just learn one thing and then apply to other. So what we can do is, for these two, like we will say A modulo M and fill in the blanks. Let's make a better box. Okay, so and b percent m, b percent not b modulo m, and whole modulo m. So this gives us our final answer. This is for a plus b, and for a minus b, what we will do is a minus b modulo m. This follow this formula. It's a bit longer than previous two, so you have to learn it obviously. A modulo m minus b modulo m. Okay, not this m, this m modulo m. Okay, so this was the same like this, but now plus m modulo m. This is the change here. So I think we got it. So now let's first do what we do every time, that this will get sorted. Okay, so this is good and enough. Now what we will learn is binary exponentiation. So first of all, let me remove this from here. Now we will study binary exponentiation. Binary exponentiation. Binary expo. Okay. So this is nothing but, we can say this is a question of recursion. Like we know a to the power m, what we can write is a to the power m by 2 into a to the power m by 2 if it is even. What even? M is even. If m is odd, writing it here only, m is odd. Okay, so this what we do. And okay, though we will study recursion later, but we can study it here. We can study this here because it will be used in many competitive programming questions. So let's try to create a function first, like int. We will study again if possible in recursion. Int power a comma m. So now if m equals no, actually let's what do, let me do this first. This is a bit tricky question, so what we'll do is we first find, and not even doing this actually, if m percent 2 m modulo 2 equals 0, that is m is even. So return not this, return power a comma m by 2 into power a comma m by 2. Else we will do the same thing but differently. We will do what we said above in even and odd cases. So we will first adopt this one, just this multiplied by a. Got it? Okay, so I think now our binary exponentiation is completed, and what we should know is inbuilt power function that is given in C++ HTL that doesn't do binary exponentiation. So it is very inefficient to use that one. Instead we will create one binary exponentiation power function and we will use that one. Okay, understood? I know. First making this in normal mode and then doing this thing. So there is another thing called modulo exponentiation, in which we will just be finding the modulo of this a to the power m. Okay, it's nothing but just modulo of a to the power m. But to prevent this from, we will do this for large numbers. Like I should write, okay, let me first send this to previous page. Okay, so modulo exponentiation, what we'll do in this is we will find a to the power m, and we'll do this for large numbers, because in large numbers this will become integer overflow, but we have been asked to find its modulo, so we can't first find this and then take modulo because it will get integer overflow. So to prevent from that, we will normally take the modulo of this. So we will do nothing but just be using this, that if m percent 2 equal 0, that is if m is even, then we will simply do a to the power b by 2 into a to the power b by 2. This will be a number and we will just take percent m. Else then it becomes a bit longer because a by 2 into a by 2, and then we also have into a as other term. So by using the modular arithmetic of multiplication, we will first take modulo of this multiplied by a modulo m and whole modulo m. It's that simple. Okay, so first let me make it smaller and then tell you what changes you need to make in that previous code of binary exponentiation to make it modular exponentiation. So we will just where we written power a comma m by 2 into power a comma m by 2, we will just to be writing this percent m if m is even. Okay, and else then it becomes longer power a comma m by 2 into power a comma m by 2 percent m into a percent m. Okay, here also we got integer overflow, I mean line overflow. Percent m. Got it? So this is the only change that we have to make in previous code. Nah. So just put this and then taking complete and decreasing its size. I think I have to decrease it even more. Okay, that's good. Now taking this completely okay, so integer overflow obviously. Okay, so we have this now. Now what we need to study is now we will do test for primality. So what is primality? Primality is to check whether a number is prime or composite. So test for primality. Primes as composite. Okay, so there are three ways to do this. For now we will just study one. First is triad division, second is Wien factorization, and third is of course sieve of Eratosthenes. Okay, so we will just study triad division here. So what is triad division? If we go into the theory part. So trial division is nothing but dividing a number until with a prime number till we can't divide it anymore. So what I want to say, let me explain it with an example like 24. So 24 by 2, 12. Still 12 is divisible by 2, so 12 by 2 is 6. Still 6 is divisible by 2, 6 by 2 is 3. Okay, so now 3 is not divisible by 2, so it is divisible by 3, so simply 3 by 3 is 1. And when we get 1, we come out of the loop. So what we can print here is 2 into 2 into 2 into 3. This is 24. So we will do this in the trial division method. How are we gonna do this? This is the main topic. So let's first decrease the size of this. Oh no. Okay, so just decreasing the size of this. Okay, so now what will be the code look like? How will the code look like? So it will look like let's write complete. So for I equals to 2, be careful here, I into I less than equals to n, and I will explain the reason soon. I plus plus. Let's first look at the code. Maybe you are understanding what I'm doing right now. You are understanding what I'm doing right now. So, and I have explained you the logic. Now we are writing just the code part. And if still n is not equals to 1, this means n is okay, so it means n is prime number. Okay, so cout n. Got it? So this is the code right here. Now first of all, let me make it smaller and then tell you why we write this I into I thing. So we wrote this I into I thing because we take its square root, I less than equals to, so it will be approximately 4. So if we see, like when we go to back page, what we see is we only need to iterate till 3, then we get it. Then we obviously get this code. Like before root n we will get all prime numbers. Okay, the prime factors. There is no prime factors after root n due to the fact that if suppose we have greater than, let's consider a number a, we will iterate it till root a. But if we iterate it till a plus 2, then if this number is a prime number, then a plus 2 into, then dividing, let me say here, dividing a with a plus 2 will give 0. If root a plus 2 is prime, then this condition will also come. And obviously any number after a dividing with the root, we will get not 0. We can't say 0 because it will be lesser than root a, not 0. Obviously, sorry, not 0, lesser than root a. So if it is lesser than root a, then we must have got this factor already occurred before root a. So we only need to iterate till square root a. Understood? So now just writing this explanation in previous page. So now we have done the test of primality. Now let's study GCD. So GCD, we will use the Euclid algo, or just use this HCF function given in STL. HCF given in STL. Okay, so we will not go deep inside that. Instead, what we will do is learn some properties of GCD. So what are some properties? First of all, LCM of A and B is equals to A into B GCD A comma B. Okay, but LCM of A comma B comma C is equals to LCM of A comma B comma C, and not A into B into C by HCF of A comma B comma C. This is completely wrong. Okay, so this is the first thing I want to mention. There are many more properties left. Let me just small it and then tell you. So what are some properties left? These are just one of the property. Other is GCD A comma B equals to minimum of let me make you understand this in few seconds. Okay, first let me write all the properties. Okay, so now I will be saying what I wrote here. It's not copy paste, obviously I wrote it in front of you. So what's written in here is that so what I wrote in here is that for each prime number GCD will be minimum of prime of A and prime of B to the power A to the power B. Okay, so let me make it clear to you with an example, like for GCD of 24, 18, and writing its prime factors as 2 to the power, what was it, 3 into 3, and what was it, 2 to the power 1 into 3 to the power 2. Okay, so what will be the HCF of these two? For first term, HCF will be 2 to the power 1. For second term, HCF will be 3 to the power 1. So what will be the HCF of these two? 9. Okay, and for LCM, what will be the LCM? 2 to the power 3 and 3 to the power 2. This is okay, LCM, and this is HCF. Only this is written here, nothing else. So now just taking its copy here. Okay, so before that we also must study that GCD of a number and just 1 plus number is always 1. We can understand it. Okay, and this is the same thing I wrote here, like I should mention it that this is the same thing. Okay, so now everything's done. GCD is also over. So these are not DSA, but these are some fundamentals that will be required in competitive programming. There are some more, like here we have the bitwise operations. Let me first take it back and then talk about this bitwise functions. Okay, so now we have to study the GCD part. Not GCD, but the bitwise functions part of bitwise operations. So some common bitwise operations that we'll be using in competitive programming are to check if the number is odd. So what I do is just copy paste this thing here and then just explaining it to you. Okay, so let's start. I will not write anything here, but just highlight the things and explain it to you. Check if the number is odd. Bad color. Let's take something lighter. It's still not that light. Okay, so what can be more lighter than the yellow? What the? That's not okay. So let's not do this and just underline the thing with red mark. This is for checking if this thing is odd. If kth bit is set. So if we use this in while loop, then we can iterate k from 0 to something like to the end of the number. Okay. So counting set bits. Nice. Till we get okay. So how we gonna do this? Let's first think a bit. Okay, so I got one logic to find this. So how we can find it's that first we will use this from 0 to n, and n can be calculated by number of set bits, and we'll also keep a count. So we will maintain a count variable till count reaches count बराबर 0 to count equals n. Okay, then iterate k from 0 number of set bits, okay, from 0, and increment it. I know this. So for counting number of set bits, we'll use this, iterate it and increment it, then we get this. Okay, increase the count for each set bit. Okay, so now flip the kth bit. You can flip the kth bit too. If we got this, then we can obviously change this too, but it is a shortcut of flipping kth bit. Obviously it is not that easy to learn these things, so just learn what we can do, and then whenever we need, we will just check this thing. Okay, set and unset kth bit. Instead of XOR, use odd and end. Okay, so just set and unset bit, kth bit. We will use this. Check if the number, okay, this one is very important. To check if the number is power of 2, we will use this. Just learn this and you can think about this on your own, why it is possible. Okay, so this one is expansion of a plus b. I don't know. It is good for solving many problems, but I have not countered any problems yet. This list is given by another person, like he is a software engineer in Google and a master in Codeforces, so maybe he has countered this thing. So just keep it in mind and nothing else. Just use this 6 things for now and keep it in mind this 7th thing. I am not going to start this, but yes, this one is start and this one is start. This one is 2 star. This one is 1 star. This one is 5 star because it prevents from integer overflow things. Actually not 5 star, it is also 3 star because I consider 3 star as top thing. Okay, so I can't compare between these two things. Okay, so maybe I should give both 5 star. Okay, so this is the thing. Let me check what else is remaining in this. So what we can do more is, let me change the color of pen and write 8 toggle the ith bit. Toggling means 0s to 1 or 1 to 0, and how we gonna do this is x XOR okay, so I think we have got this here, snip the kth bit. Okay, so we don't need this toggle thing. I think it has covered most of the things. Okay, so yeah, something is more given in this, so let's write this first. 2 to the power n is nothing but, okay, so now next thing is we can get something like this from okay, uppercase lowercase conversion. Upper lower conversion. So what we do right now is just subtract the thing, like if uppercase can be given and we have to convert it lowercase, we divide it with according to the ASCII code. I think it is 32. Yes, most probably it is 32. So we do this thing, but alternatively what we can do is just make the 5th bit set to convert it to subtract, or I think add 32. Okay, so what we can do is just make the 5th bit set to convert the upper to lower. Make fifth bit set. How we gonna make it? By just character d equals to c. This is just an example, an application of this set and unset kth bit. Okay. Application of set bit. Okay, so now I think I should just wrap the whole thing and make it short again. So there is another thing, bit masking is given. We will study bit masking. So what is left for now? We will many things are left, but what we're gonna do in study in next class is bit mask pointers. Just these two things. We will not going to study the oops in these lectures. Okay, so keep it in mind. Let's wrap up this session here. Thank you. Bye.